Right, so this problem gives us a structure and a whole lot of information about the structure, not a whole lot of which we need to actually answer the problem. So it's telling us that this is a pheromone, but really let's get to the crux of the question. So it tells you, here's the structure. It contains a bicyclic acetal. So here we're getting to the organic chemistry part of it, and we're being asked which carbon is the acetal carbon. So when you make an acetal out of, say, an aldehyde or a ketone. So you have the carbonyl form. And when it's converted to an acetal, you can recognize the acetal carbon by finding the carbon that has the 2 single bonds to oxygen. So that's your acetal carbon. So that's what we're going to look for in this structure. And then we're going to take this a couple steps further and say, all right, well, what if we wanted to hydrolyze the acetal to go back to the carbonyl? Because these reactions are completely reversible. So if you exclude water and use an excess of your alcohol, you're going to get this way. And if you add aqueous acid, it's going to go back to the carbonyl compound. And so that's why it's important for us to be able to identify these acetal carbons. So if we take a look, this should actually be a really fast problem to solve, because hopefully we will see very quickly that this carbon atom B has these 2 single bonds to oxygen. Okay, so in terms of this question, that's the end of the question, but we want to keep going with this and see if we can draw the product of the hydrolysis. So here's what we want to do. We want to grab a trusty pencil and redraw this structure to come up with the hydrolysis product. So let's go ahead and do that. I'm going to use a few tricks, taking a few shortcuts here. So I just drew my 6-membered ring and then erased part of it to make the oxygen in there. I'm going to do the same thing to put in the other part of the structure, because we've got this 2-atom bridge. One of those atoms happens to be an oxygen. There we go. And so we've got the same structure. All right, and so by recognizing the acetal carbon, what we can do is we can say, okay, well, that's the carbon that used to be the carbonyl. So your acetal carbon was the carbonyl. Okay, and these oxygens came from the alcohol. So what we need to do, right, is we need to break these bonds. So here we can do this with an eraser very easily. So if we're going backwards, we're going to say, okay, what we started with, these 2 oxygens were definitely alcohols. So it's a little tough to squeeze them in there, but we can see them. And this carbon that we identified as the acetal carbon was previously a carbonyl. So if we're taking this reaction backwards, that would be the product. So this is the acetal hydrolysis product. And now you're not likely to see, if you're asked to do an acetal hydrolysis, you're not likely to see it all kind of bunched up in this shape that looks like what it just came from. We usually take these acyclic molecules and straighten them out. So let's do that. So let's go ahead and number. I am just numbering the longest carbon chain, not for IUPAC or anything like that, but just for my own knowledge. When I want to draw this out, I want to know how long of a chain I want to draw. So it looks like I need a 7 carbon atom chain. So 1, 2, 3, 4, 5, 6, 7. Okay, I'll go ahead and number these so we can track them. And all my goal is here is to take this structure and draw it in a way that would be more likely what we would see. Okay, a typical bond line structure. So now that I've got that 7 carbon atom chain, I just want to make sure that everything else that's attached to these 7 carbon atoms is still reflected here. So I can see that on carbon 2 is the carbonyl. Nothing on carbon 3, 4, 5. And then when I get to carbon 6, I have a methyl group and an alcohol. So a methyl group and an alcohol. And then on carbon 7, I have the other alcohol. So this was an intramolecular reaction to form this acetal. Okay, and so this would be reversible to go from the acetal, so the acetal hydrolysis could go to here. If you kept water out and put a dry acid catalyst, you could go backwards to get to that acetal.